So today we're talking about reactivity of metals. Basically, we are going to go through what are minerals, what are the use of minerals, and the reactivity series, which you will learn later in the video. It's a very important part of this chapter, and also some basics of the extraction of iron. So to get things started, we need to understand what are minerals. So minerals are solid elements and compounds that you can find in nature. So they have definite crystalline structures and chemical compositions. So it means that the compositions, the elements they make them, is not changed in whatever circumstance. It has a definite chemical composition. It has a definite crystalline structure. So what are the form of minerals? Well, minerals comes in two forms. Minerals come in the form of elements, which means the mineral itself is in its elemental state, which means there's only one element within the chemical composition of it. Stuff like gold, silver are elements because they exist in nature as gold and silver. The second type is compounds. Compounds are a combination of several elements. So compound minerals, they exist as a compound, as a combination of several elements, but it requires to be purified and extracted in order to get the metal we want. Stuff like hematite, which is iron trioxide. Within hematite, the compound has iron 3 and oxygen. It has iron and oxygen, so in order for us to get iron, we need to extract the iron out of hematite. Same goes with bauxite, pyrite, and calcite. We're going to come into a little experiment here. So the experiment is, how do we determine the composition of calcium carbonate? So, okay, let's assume that you don't know what is calcium carbonate, what it has, but you can actually look at it. It has calcium, carbon, and oxygen, but let's just assume that you don't, all right? You look at these two experiments. The first one is you react calcium carbonate with hydrochloric acid. The second one is you decompose calcium carbonate by heating it, and then there's lime water. There's actually lime water in both, right? So look carefully at the diagram. So there's going to be a few questions that are going to come out in the exam that will resemble similar questions. Most of the questions they ask are almost the same, right? You're going to ask what's the use of lime water. So if you remember, I think it was Form 2 that the test for the gases. So quick recap: to test for oxygen, you use a splint that is burnt out. So oxygen rekindles a glowing splint. Hydrogen, so you bring a lighter splint into the mouth of test tube containing hydrogen. It lets out a pop sound. So that's how you determine oxygen and hydrogen. Yes, I repeat. So to determine the gas is hydrogen, you bring a lighter splint into the mouth of the test tube containing hydrogen gas, or quote unquote hydrogen gas because you don't know. If it lets out a pop sound and it extinguishes the flame, then that is hydrogen gas. Oxygen gas rekindles a glowing splint. So if you bring a glowing splint to the mouth of the test tube containing quote unquote oxygen, because you don't know, the splint will actually the flame will actually rekindle. So lime water. Lime water is to test for the presence of carbon dioxide. So lime water is basically calcium hydroxide. So which means if you put in carbon dioxide, sorry. So lime water is calcium hydroxide. So if you put in carbon dioxide in, then that means the reaction will occur and then they will produce calcium carbonate and water. So they will see white precipitate within the lime water itself. So that's the indicator that carbon dioxide is present. So it turns cloudy, which means there are precipitates within lime water when reacted with CO2. So what are the products of the reaction? The products of the reactions are these. So calcium carbonate reacts with hydrochloric acid, produces calcium chloride. Yes, because you look at the hydrochloric acid, it has hydrogen and chloride. It has a hydrogen ion and a chloride ion. And then calcium carbonate has the carbonate bicarbonate ion, which is a CO3, it's actually 2 minus, and calcium. So calcium react with chloride to form calcium chloride. Actually, hydrogen react with the bicarbonate ion to form hydrogen bicarbonate, but hydrogen bicarbonate is unstable. I repeat, hydrogen bicarbonate is unstable. So it will break down into water and carbon dioxide. And the second one is basically you breaking down calcium carbonate into into two forms, which is calcium oxide and carbon dioxide. So you just release the carbon dioxide from within the calcium carbonate itself. So now get into the main part of the video, yes? Reactivity series of metals. So it is a series that determines how reactive a metal is to oxygen. Okay, to repeat, a series that determines how reactive a metal is to oxygen. So that means if you put the metal out in the open to react it with air, because air contains oxygen, it determines how reactive it is. So if you put it in air, it will form metal oxide, said metal oxide. So how easy it is to form said metal oxide is determined by this series. And it also determines a lot of other factors, and I will get into it later. So it also determines the ability of the metal to displace other metals in the chemical reaction, or hydrogen or carbon. Okay, so let's say there's a reaction between potassium, and hydrochloric acid. Yes, and then okay, actually, I actually should use the okay. All right, so let's say there's potassium and calcium hydroxide and hydrochloric acid, right? So how do you determine that this is able to react to cause a reaction within this? So that means if a reaction needs to occur, this potassium must take the place of the hydrogen and form potassium chloride. But each metal has different reactivity. So that means there are some the reactivity is not strong enough to displace, so there's no reaction that occurs. So the series determine which metal can displace the other metal or hydrogen or carbon in a reaction. If it's able to displace, reaction occurs, as I said. If, like, for example, you go back to the potassium and hydrochloric acid, if potassium is strong enough to displace the hydrogen, then reaction occurs. Potassium chloride is formed, and then hydrogen is released because it is released. Yeah. So let's get into the actual series now. So now we get to the most important part, which is the actual reactivity series. So as you can see, it's written down in symbols. So it goes in accordance with the sequence: potassium, sodium, calcium, magnesium, aluminium, zinc, iron, tin, lead, hydrogen, copper, mercury, silver, platinum, and gold. So you can see there's hydrogen present here. As I say, hydrogen is very important in the reactivity series along with carbon, but it's not discussed here yet. It's because hydrogen, all of the acids contain hydrogen. You think about it. Hydrochloric acid, HCl, sulfuric acid, S2SO4, nitric acid, HNO3. So these are negative, or the anions, negative ions. Yes, negative ions can be chloride, sulfide, and nitrite. But the positive ion, which is the cation, is always hydrogen. So in order for a reaction that is in an acidic condition, which means something else is reacting with an acid, in order for that reaction to occur, something needs to displace the hydrogen. Yes, if nothing is getting displaced, nothing is happening, then the reaction doesn't occur. So we refer to this reactivity series to see which metal is able to displace hydrogen, basically take its place and cause a reaction to occur. So from the left to the right, the left is the most reactive and the right is the most unreactive. So potassium is actually the most reactive of all metals. So potassium is basically king, right? You can think about this. Potassium is basically king. He can take anything he wants. So let's say the anion is the object, the thing that we crave. Let's say is money, right? So potassium is the king. So he basically can take everything he wants. So every metal under him, or in the case metal and hydrogen, whatever they have, he can take it. It doesn't matter if it's sodium chloride. That actually sodium is quite close. If we react with potassium, takes its place, forms potassium chloride, and then sodium is liberated. Magnesium chloride, put in potassium, forms potassium chloride, and then it liberates magnesium, right? So potassium itself is the most strongest metal, or let's say the most reactive metal within this series. And as we go down, sodium. So sodium is like the beta. So basically anything under him is able to get, but whatever potassium has, no, he can't get it because potassium is the king. Remember, potassium is the king. Whatever potassium has, he can't get it. But calcium, yeah, of course. Magnesium, of course, right? But sodium can only get anything from below. So from this sense, if this entire block, yes, this entire block is above hydrogen. So any of these metals reacting with an acid will form a salt because, as I said, HCl, H2SO4, the anions and plus metal is a salt, right? Because anything that is not acid or alkali is a salt, basically. But we'll get into organic solvents later, but that's the trace, right? If there's an cation, there's an anion, and then it's not alkali or acid, that means it's a salt. So anything above hydrogen, it can react with hydrogen. But which reaction happens fastest? Of course, it's the strongest one that happens fastest, the weakest one that happens slowest. I repeat, the fastest one happens, the strongest one happens the fastest. The reaction is bigger and faster, while lead is the weakest one, which means the reactivity isn't that high compared to hydrogen. That means the rate of reaction of the entire reaction itself is slower. And say below hydrogen, copper, mercury, yes. So let's say we can put hydrochloric acid, copper. Theoretically, if the reaction does occur, you get copper chloride and hydrogen will be released, right? But however, copper is not reactive enough to displace hydrogen. So that means there is no reaction, no products are formed. They'll just be in their reactant stage. Nothing will happen because copper is not strong enough to displace hydrogen, right? All right, let's get into the next slide before I use too much of my time. All right, so we're getting into some of the questions. So these are much more popular questions, and it tests you on the theory of the reactivity series that you've just learned. So I get the reactivity series up on screen right now. So what are the products of calcium chloride and potassium? Okay, before you think about anything, right, you can think about all the products are probably calcium chloride, potassium chloride, and calcium, right? Because displacement and everything takes its anion, reaction occurs. But you have to ask yourself before all of that is, will the reaction occur? Because if the reaction doesn't occur, then there will be no products. You must understand that. So we can take a look at the reactivity series, the position of potassium and calcium. So calcium is actually lower than potassium. As I said, potassium is king. He can take anything he wants, any anion he wants from everything that's under him. So will the reaction occur? Of course, because calcium is weaker. And what is anion? Chloride. So potassium will take chloride to form potassium chloride. Sorry, potassium chloride is actually KCl. I did a thing there, and then calcium is liberated. It's basically neglected. I can't say neglected, but it's like he's liberated. Yeah, it's like he was tossed aside. So because potassium is more reactive than calcium, this is the official explanation. How we can write it out is potassium is more reactive than calcium, so potassium displaces chloride from calcium. That's the entire thing. All right, quick water break there. Okay, so now we get into the extraction of metals, which I said you're going to learn the basics of extracting metal from the compounds like bauxite, like hematite, right? Hematite is iron trioxide. So you need to get the iron out of iron trioxide. So extraction of metals, you need to obtain metals from the ores, which means metals that are not elements, they are compounds, like bauxite, like hematite, which is iron trioxide, and aluminium oxide. You can refer to the previous, the earlier parts of this video to see. But yes, so extraction of metals is you obtain metals from the ores, and the reactivity series comes in because the ores, well, the ores have certain metals, yes. So like iron trioxide, it has iron. Aluminium oxide has aluminium. Yeah. So even potassium itself isn't an elemental metal. Yes, you need to extract it. So now what comes into play in the extraction of metals is carbon, because we can't necessarily use hydrogen to extract metals, although it's quite plausible because hydrogen is quite low in the reactivity table. You need something bigger to displace whatever it is combining with the metal, say iron trioxide, so oxygen is combining with iron. You need something larger to displace the oxygen from the iron so that we can get pure iron. But we can't use other metals because, well, other metals are in compounds themselves as well. So how do you get them out of the compound? You need something that exists as an element in nature, but it isn't a metal. So we've gone for carbon, and we found that carbon is actually more reactive than hydrogen, in the sense that carbon is more reactive than zinc but less reactive than aluminium. So the position of carbon in the reactivity series is between aluminium and zinc. So now the reactivity series turns into KNaCa, MgAO, ZnFeS, and PbH, and then so on. Okay, so now we get into the method of extraction of each metal. The method of extraction of the metal is determined by the position of the metal in the reactivity series. So the reactivity series plays a big role in this, as you can see. I'll put the reactivity series on screen now. Carbon is excluded because, well, we don't really react it with pure carbon unless we want to extract the metal itself. But hydrogen is included within the reactivity series, but that's for another day. So we can split it into 4 parts. We exclude hydrogen from the equation because hydrogen is not a metal. The first part is the hyperreactive metal, which I could categorize as hyperreactive, which means it's very, very reactive. So we use electrolysis to extract the metal, in the sense that, you know how electrolysis of water is conducted, where you separate the hydrogen and the oxygen from the water molecules via electrolysis. Yes, it's the same thing. So we separate the compounds that contains potassium and another anion, right? Which is in molten state, which means it's liquid compound, but it's not an aqueous solution, it's molten. And then we extract it via that method. But because they are very reactive, you can use electrolysis, but anything below aluminium becomes a bit less reactive, I would say. So that's where carbon comes in, because carbon's more reactive than zinc and and iron and whatnot, right? So copper and mercury, you can use heating because or you can displace them using hydrogen. Because now, when you reach copper and mercury, now hydrogen is more reactive than them. So whatever compound they form, you pass hydrogen in, hydrogen is going to displace the anion, and you're left with pure copper or pure mercury. And the last part is silver, platinum, and gold. They already exist as elements because they are so unreactive that they don't react with anything, so they don't form compounds. It comes on screen that zinc, iron, tin, and lead is extracted via reduction by carbon because they have lower reactivity than carbon itself. Alright, so now we got into the reaction within the furnace itself, right? So what happens within the furnace? Well, you know stuff is getting burned, you throw in coke, which is carbon, okay? So you throw in carbon into the furnace, limestone, whatever. What happens within it? Yeah? Ask yourself you have to ask yourself what happens within anything in chemistry, right? So what happens? What happens in the elemental stage? So you need carbon as a reducing agent. So you reduce. Okay, so you picture the idea of reduce. You take a bigger stuff and then you make it into smaller stuff. Same with the compound. So hematite is iron trioxide. You reduce hematite into iron, so you take away oxygen. So you reduce hematite into iron, which is pure iron, right? So carbon and carbon monoxide is pumped into the furnace itself. So it forms carbon dioxide, and carbon dioxide, because there is oxygen within it, so it forms carbon dioxide. Carbon dioxide reacts with carbon itself to form carbon monoxide, but there's excess carbon, so there is carbon monoxide and carbon, and both of them are reducing agents. So it makes hematite, it reduces hematite from iron trioxide into iron. So now we get into the meat to grindy question. What is slag? You remember from the picture you see of the blast furnace, there is molten slag coming out. So what is slag? I told you that slag is like the waste products, right? It's like the excrement products of the process because you don't really want anything else than iron itself. So slag is calcium silicate in chemical terms. So it's silica and calcium is formed by the impurities in iron ore and calcium oxide. So you remember we have limestone, yes, we have limestone. And we have the impurities within the iron ore itself, which may be silicon dioxide or like oxygen or stuff like that, right? So you throw in calcium oxide in, which is the limestone. It reacts with all these impurities to form calcium silicate. It forms into a compound, and then the entire compound gets removed so that only the iron remains. So the formation of slag is calcium carbonate, which is limestone. It decomposes into carbon dioxide and calcium oxide decomposition because, as I say, it's high temperature. Everything here happens in a very high temperature. It breaks down into calcium oxide and carbon dioxide, and then the calcium oxide from the reaction reacts with silicon dioxide, which is one of the impurities within the iron ore, to form calcium silicate. There we go. So that's the slag, and whatever impurities there is in the iron ore gets removed in the form of slag. That's why we need calcium carbonate in the furnace. So this is what you have to learn within this chapter. I hope you enjoy it. And as always, stay classy, stay cool, and don't be a fool. Thank you for watching.